Section 15 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gary Gilbert, 2007. Familiar Letters on Chemistry by Justus, Liebig. Letter number 15. My dear Sir, you are now acquainted with my opinions respecting the effects of the application of mineral agents to our cultivated fields, and also the rationale of the influence of the various kinds of manures. You will, therefore, now readily understand what I have to say of the sources whence the carbon and nitrogen, indispensable to the growth of plants, are derived. The growth of forests and the produce of meadows demonstrate that an inexhaustible supply of carbon is furnished for vegetation by the carbonic acid of the atmosphere. We obtain from an equal surface of forest or meadowland, where the necessary mineral elements of the soil are present in a suitable state, and to which no carbonaceous matter whatever is furnished in manures, an amount of carbon, in the shape of wood and hay, quite equal, and ofttimes more than is produced by our fields in grain, roots, and straw, upon which abundance of manure has been heaped. It is perfectly obvious that the atmosphere must furnish to our cultivated fields as much carbonic acid as it does to an equal surface of forest or meadow, and that the carbon of this carbonic acid is assimilated, or may be assimilated, by the plants growing there, provided the conditions essential to its assimilation and becoming a constituent element of vegetables exists in the soil of these fields. In many tropical countries, the produce of the land in grain or roots during the whole year depends upon one rain in the spring. If this rain is deficient in quantity or altogether wanting, the expectation of an abundant harvest is diminished or destroyed. Now it cannot be the water merely which produces this enlivening and fertilizing effect observed, and which lasts for weeks and months. The plant receives, by means of this water, at the time of its first development, the alkalis, alkaliners, and phosphates necessary to its organization. If these elements, which are necessary previous to its assimilation of atmospheric nourishment, be absent, its growth is retarded. In fact, the development of a plant is in a direct ratio to the amount of matter it takes up from the soil. If, therefore, a soil is deficient in these mineral constituents required by plants, they will not flourish even with an abundant supply of water. The produce of carbon on a meadow, or an equal surface of forest land, is independent of a supply of carbonaceous manure, but it depends upon the presence of certain elements of the soil, which in themselves contain no carbon, together with the existence of conditions under which their assimilation by plants can be effected. We increase the produce of our cultivated fields, in carbon, by a supply of lime, ashes, and marl, substances which cannot furnish carbon to the plants. And yet it is indisputable, being founded upon abundant experience, that in these substances we furnish to the fields elements which greatly increase the bulk of their produce and consequently the amount of carbon. If we admit these facts to be established, we can no longer doubt that a deficient produce of carbon, or in other words, the bareness of a field, does not depend upon carbonic acid, because we are able to increase the produce to a certain degree by a supply of substances which do not contain any carbon. The same source whence the meadow and the forest are furnished with carbon is also open to our cultivated plants. The great object of agriculture, therefore, is to discover the means best adapted to enable these plants to assimilate the carbon of the atmosphere which exists in it as carbonic acid. In furnishing plants, therefore, with mineral elements, we give them the power to approximate carbon from a source which is inexhaustible, whilst in the absence of these elements the most abundant supply of carbonic acid, or of decaying vegetable matter, would not increase the produce of a field. With an adequate and equal supply of these essential mineral constituents in the soil, the amount of carbonic acid absorbed by a plant from the atmosphere in a given time is limited by the quantity which is brought into contact with its organs of absorption. The withdrawal of carbonic acid from the atmosphere by the vegetable organism takes place chiefly through its leaves. This absorption requires the contact of the carbonic acid with their surface, or with the parts of the plant by which it is absorbed. The quantity of carbonic acid absorbed in a given time is in direct proportion to the surface of the leaves and the amount of carbonic acid contained in the air. That is, two plants of the same kind and the same extent of surface absorption, in equal times and under equal conditions, absorb one and the same amount of carbon. In an atmosphere containing a double portion of carbonic acid, a plant absorbs, under the same condition, twice the quantity of carbon. Boussingault observed that the leaves of the vine, enclosed in a vessel, withdrew all the carbonic acid from a current of air which was passed through it, however great its velocity. Dumas Lecon, page 23. If, therefore, we supply double the quantity of carbonic acid to one plant, the extent of the surface of which is only half that of another living in ordinary atmospheric air, the former will obtain and approximate as much carbon as the latter. Hence results the effect of humus and all decaying organic substances upon vegetation. If we suppose all the conditions for the absorption of carbonic acid present, a young plant will increase in mass in a limited time only in proportion to its absorbing surface. But if we create in the soil a new source of carbonic acid by decaying vegetable substances, the roots absorb in the same time 3 times as much carbonic acid from the soil as the leaves derive from the atmosphere. The plant will increase in weight fourfold. This fourfold increase extends to the leaves, buds, stalks, etc. And in the increased extent of the surface, the plant acquires an increased power of absorbing nourishment from the air, which continues in action far beyond the time when its derivation of carbonic acid through the roots ceases. Humus, as a source of carbonic acid in cultivated lands, is not only useful as a means of increasing the quantity of carbon, an effect which in most cases may be indifferent for agricultural purposes, but the mass of the plant having increased rapidly in a short time, space is obtained for the assimilation of the elements of the soil necessary for the formation of new leaves and branches. Water evaporates incessantly from the surface of the young plant. Its quantity is in direct proportion to the temperature and the extent of the surface. The numerous radical fibrulae replace, like so many pumps, the evaporated water, and so long as the soil is moist or penetrated with water, the indispensable elements of the soil dissolved in the water are supplied to the plant. The water absorbed by the plant evaporating in an aeriform state leaves the saline and other mineral constituents within it. The relative proportion of these elements taken up by a plant is greater, the more extensive the surface and more abundant the supply of water. Where these are limited, the plant soon reaches its full growth, while if their supply is continued, a greater amount of elements necessary to enable it to appropriate atmospheric nourishment being obtained, its development proceeds much further. The quantity or mass of seed produced will correspond to the quantity of mineral constituents present in the plant. That plant, therefore, containing the most alkaline phosphates and earthy salts, will produce more or a greater weight of seeds than another which in equal time has absorbed less of them. We consequently observe, in a hot summer, when a further supply of mineral ingredients from the soil ceases through want of water, that the height and strength of plants, as well as the development of their seeds, are in direct proportion to its absorption of the elementary parts of the soil in the preceding epochs of its growth. The fertility of the year depends in general upon the temperature and the moisture or dryness of the spring. If all the conditions necessary to the assimilation of the atmospheric nourishment be secured to our cultivated plants, the action of humus then, as we have explained it above, is chiefly of value in gaining time. In agriculture this must ever be taken into account, and in this respect humus is of importance in favoring the growth of vegetables, cabbages, etc. But the cerealia and plants grown for their roots meet on our fields in the remains of the preceding crop with a quantity of decaying vegetable substances corresponding to their contents of mineral nutriment from the soil, and consequently with a quantity of carbonic acid adequate to their accelerated development in the spring. A further supply of carbonic acid, therefore, would be quite useless without a corresponding increase of mineral ingredients. From a morgen of good meadowland, 2,500 pounds weight of hay, according to the best agriculturists, are obtained on an average. This amount is furnished without any supply of organic substances, without manure containing carbon or nitrogen, by irrigation and the application of ashes or gypsum. Double that amount may be grown, but assuming 2,500 pounds weight of hay to be the maximum, we may calculate the amount of carbon and nitrogen derived from the atmosphere by the plants of the meadow. According to elementary analysis, hay, dried at a temperature of 100 degrees Reaumur, contains 45.8% of carbon and 1.5% of nitrogen. 14% of water retained by the hay, dried at common temperatures, is driven off at 100 degrees. 2,500 pounds weight of hay, therefore, corresponds to 2,150 pounds dried at 100 degrees. This shows us that 984 pounds of carbon and 32.2 pounds weight of nitrogen have been obtained in the produce of 1 morgen of meadowland. Suppose that this nitrogen has been absorbed by the plants in the form of ammonia. The atmosphere contains 39.1 pounds weight of ammonia to every 3,640 pounds weight of carbonic acid, equals 984 carbon, or 27%. Or in other words, to every 1,000 pounds weight of carbonic acid, 10.7 pounds of ammonia, that is, to about 1/100,000th the weight of the air, or 1/60,000th of its volume. For every 100 parts of carbonic acid absorbed by the surface of the leaves, the plant receives from the atmosphere somewhat more than 1 part of ammonia. With every 1,000 pounds of carbon we obtain from a meadow 32/7 pounds of nitrogen from cultivated fields in wheat, 21.5 pounds of nitrogen, oats 22.3 pounds of nitrogen, rye 15.2 pounds of nitrogen, potatoes 34.1 pounds of nitrogen, beetroot 39.1 pounds of nitrogen, clover 44 pounds of nitrogen, peas 62 pounds of nitrogen. Bossingalt obtained from his farm at Bechelbronn in Alsace in 5 years the shape of potatoes, wheat, clover, turnips, and oats, 8,383 of carbon and 250.7 nitrogen. In the following 5 years, as beetroot, wheat, clover, turnips, oats, and rye, 8,192 of carbon and 284.2 of nitrogen. In a further course of 6 years, potatoes, wheat, clover, turnips, peas, and rye, 10,949 of carbon, 356.6 of nitrogen. In 16 years, 27,424 carbon, 858 and one half nitrogen, which gives us for every 1,000 carbon 31.3 nitrogen. From these interesting and unquestionable facts, we may deduce some conclusions of the highest importance in their application to agriculture. 1. We observe that the relative proportions of carbon and nitrogen stand in a field relation to the surface of the leaves. Those plants in which all the nitrogen may be said to be concentrated in the seeds, as in cerealia, contain on the whole less nitrogen than the leguminous plants, peas, and clover. 2. The produce of nitrogen on a meadow which receives no nitrogenized manure is greater than that of a field of wheat which has been manured. 3. The produce of nitrogen in clover and peas, which agriculturists will acknowledge require no nitrogenized manure, is far greater than that of a potato or turnip field, which is abundantly supplied with such manures. Lastly, and this is the most curious deduction to be derived from the above facts, if we plant potatoes, wheat, turnips, peas, and clover, plants containing potash, lime, and silex, upon the same land, 3 times manured, we gain in 16 years, for a given quantity of carbon, the same proportion of nitrogen which we receive from a meadow which has received no nitrogenized manure. On a morgen of meadow land we obtain in plants containing silex, lime, and potash 984 carbon, 32.2 nitrogen. On a morgen of cultivated land, in an average of 16 years, the plants containing the same mineral elements, silex, lime, and potash, 857 carbon, 26.8 nitrogen. If we add the carbon and nitrogen of the leaves of the beetroot and the stalk and leaves of the potato, which have not been taken into account, it still remains evident that the cultivated fields, notwithstanding the supply of carbonaceous and nitrogenized manures, produce no more carbon and nitrogen than an equal surface of meadowland supplied only with mineral elements. What then is the rationale of the effect of manure, of the solid and fluid excrements of animals? This question can now be satisfactorily answered. That effect is the restoration of the elementary constituents of the soil which have been gradually drawn up from it in the shape of grain and cattle. If the land I am speaking of had not been manured during those 16 years, not more than 1/2 or perhaps than 1/3 part of the carbon and nitrogen would have been produced. We owe it to the animal excrements that it equaled in production the meadow land, and thus, because they restored the mineral ingredients of the soil removed from the crops. All that the supply of manure accomplished was to prevent the land from becoming poorer in these than the meadow, which produces 2,500 pounds of hay. We withdraw from the meadow in this way hay as large an amount of mineral substances as we do in one harvest of grain, and we know that the fertility of the meadow is just as dependent upon the restoration of these ingredients to its soil as the cultivated land is upon manures. 2 meadows of equal surface, containing unequal quantities of inorganic elements of nourishment, other conditions being equal, are very unequally fertile. That which possesses most, furnished most hay. If we do not restore to a meadow the withdrawn elements, its fertility decreases, but its fertility remains unimpaired when a due supply of animal excrements, fluid and solid, and it not only remains the same, but may be increased by a supply of mineral substances alone, such as remain after the combustion of lignaceous plants and other vegetables, namely ashes. Ashes represent the whole nourishment which vegetables receive from the soil. By furnishing them in sufficient quantities to our meadows, we give the plants growing on them the power of condensing and absorbing carbon and nitrogen by their surface. May not the effect of the solid and fluid excrements, which are the ashes of plants and grains, which have undergone combustion in the bodies of animals and of man, be dependent upon in the same cause? Should not the fertility resulting from their application be altogether independent of the ammonia they contain? Would not their effect be precisely the same in promoting the fertility of cultivated plants, if we had evaporated the urine and dried and burned the solid excrements? Surely the cerealia and leguminous plants which we cultivate must derive their carbon and nitrogen from the same source whence the gramineae and leguminous plants of the meadow obtain them. No doubt can be entertained of their capability to do so. In Virginia, upon the lowest calculation, 22 pounds weight of nitrogen were taken on the average yearly from every morgen of the wheat fields. This would amount in 100 years to 2200 pounds weight. If this were derived from the soil, every morgen of it must have contained the equivalent of 110,000 pound weight of animal excrements, assuming the latter, when dried at the temperature of boiling water, to contain 2%. In Hungary, as I remarked in a former letter, tobacco and wheat have been grown upon the same field for centuries without any supply of nitrogenized manure. Is it possible that the nitrogen essential to and entering into the composition of these crops could have been drawn from the soil? Every year renews the foliage and fruits of our forests of beech, oak, and chestnuts. The leaves, the acorns, the chestnuts are rich in nitrogen. So are coconuts, breadfruit, and other tropical productions. This nitrogen is not supplied by man. Can it indeed be derived from any other source than the atmosphere? In whatever form the nitrogen supplied to plants may be contained in the atmosphere, in whatever state it may be when absorbed from the atmosphere, it must have been derived. Did not the fields of Virginia receive their nitrogen from the same source as the wild plants? Is the supply of nitrogen in the excrement of animals quite a matter of indifference? Or do we receive back from our fields a quantity of the elements of blood corresponding to this supply? The researches of Boussingault have solved this problem in the most satisfactory manner. If, in his grand experiments, the manure which he gave to his fields was in the same state, in other words, dried at 110 degrees in a vacuum, as it was when analyzed, these fields received in 16 years 1,300 pounds of nitrogen. But we know that by drying all the nitrogen escapes which is contained in solid animal excrements, as volatile carbonate of ammonia. In this calculation, the nitrogen of the urine, which by decomposition is converted into carbonate of ammonia, has not been included. If we suppose it amounted to half as much as that in the dried excrements, this would make the quantity of nitrogen supplied to the fields 1,950 pounds. In 10 years, however, as we have seen, only 1,517 pounds of nitrogen was contained in their produce of grain, straw, roots, etc. That is, far less than was supplied in the manure. And in the same period, the same extent of surface of good meadow land, 1 hectare equals 1 Hessian morgen, which received no nitrogen in manure, 2,062 pounds of nitrogen. It is well known that in Egypt, from the deficiency of wood, the excrement of animals is dried and forms the principal fuel, and that the nitrogen from the soot of this excrement was, for many centuries, imported into Europe in the form of sal ammoniac, until a method of manufacturing this substance was discovered at the end of the last century by Gravenhorst of Brunswick. The fields in the delta of the Nile are supplied with no other animal manures than the ashes of the burnt excrements, and yet they have been proverbially fertile from a period earlier than the first dawn of history, and that fertility continues to the present day as admirable as it was in the earliest times. These fields receive every year from the inundation of the Nile a new soil, in its mud deposited over their surface, rich in those mineral elements which have been withdrawn by the crops of the previous harvest. The mud of the Nile contains as little nitrogen as the mud derived from the Alps of Switzerland, which fertilizes our fields after the inundations of the Rhine. If this fertilized mud owed its property to nitrogenized matters, what enormous beds of animals and vegetables, excavae and remains, ought to exist in the mountains of Africa, in heights extending beyond the limits of perpetual snow, where no bird, no animal finds food from the absence of all vegetation. Abundant evidence to support of the important truth we are discussing may be derived from other well-known facts. Thus, the trade of Holland in cheese may be adduced in proof and illustration thereof. We know that cheese is derived from the plants which serve as food for cows. The meadowlands of Holland derive the nitrogen of cheese from the same source as with us, i.e., the atmosphere. The milch cows of Holland remain day and night on the grazing grounds, and therefore in their fluid and solid excrements return directly to the soil all the salts and earthy elements of their food. A very insignificant quantity only is exported in cheese. The fertility of these meadows can therefore be as little impaired as our own fields, to which we restore all the elements of the soil as manure, which have been withdrawn in the crops. The only difference is, in Holland they remain on the field, whilst we collect them at home and carry them from time to time to the fields. The nitrogen of the fluid and solid excrements of cows is derived from the meadow plants which received it from the atmosphere. The nitrogen of the cheese also must be drawn from the same source. The meadows of Holland have, in the lapse of centuries, produced millions of hundredweights of cheese. Thousands of hundredweights are annually exported, and yet the productiveness of the meadows is in no way diminished, although they never receive more nitrogen than they originally contained. Nothing can be more certain than the fact that an exportation of nitrogenized products does not exhaust the fertility of a country, inasmuch as it is not the soil, but the atmosphere, which furnishes its vegetation with nitrogen. It follows, consequently, that we cannot increase the fertility of our fields by supply of nitrogenized manure or by salts of ammonia, but rather that their produce increases or diminishes in direct ratio with the supply of mineral elements capable of assimilation. The formulation of the constituent elements of blood, that is, of the nitrogenized principles in our cultivated plants, depends upon the presence of inorganic matters in the soil, without which no nitrogen can be assimilated, even when there is a most abundant supply. The ammonia contained in animal excrements exercises a favorable effect, inasmuch as it is accompanied by the other substances necessary to accomplish this transition into the elements of the blood. If we supply ammonia associated with all the conditions necessary to its assimilation, it ministers to the nourishment of the plants. But if this artificial supply is not given, they can derive all the needed nitrogen from the atmosphere, a source every loss from which is restored by the decomposition of the bodies of dead animals and the decay of plants. Ammonia certainly favors and accelerates the growth of plants in all soils wherein all the conditions of its assimilation are united, but it is altogether without effect as respects the production of the elements of blood. Where any of these conditions are wanting, we can suppose that asparagine, the active constituent of asparagus, the mucilaginous root of the marshmallow, the nitrogenized and sulphurous ingredients of mustard seeds, and of all cruciferous plants, may originate without the aid of the mineral elements of the soil. But if the principle of those vegetables
which serve as food could be generated without the cooperation of the mineral elements of blood, without potash, soda, phosphate of lime, they would be useless to us and to herbivorous animals as food. They would not fulfill the purpose for which the wisdom of the Creator has designed them. In the absence of alkalis and phosphates, no blood, no milk, no muscular fiber can be formed. Without phosphate of lime, our horses, sheep, and cattle would be without bones. In the urine and in the solid excrement of animals we carry ammonia, and consequently nitrogen, to our cultivated plants, and this nitrogen is accompanied by all the mineral elements of food exactly in the same proportions in which both are contained in the plants which served as food to the animals, or what is the same, in those proportions in which both can serve as nourishment to a new generation of plants, to which both are essential. The effect of an artificial supply of ammonia as a source of nitrogen is therefore precisely analogous to that of humus as a source of carbonic acid. It is limited to a gain of time, that is, it accelerates the development of plants. This is of great importance and should always be taken into account in gardening, especially in the treatment of the kitchen garden, and as much as possible in agriculture on a large scale, where the time occupied in the growth of the plants cultivated is of importance. When we have exactly ascertained the quantity of ash left after the combustion of cultivated plants which have grown upon all varieties of soil, and have obtained correct analysis of these ashes, we shall learn with certainty which of the constituent elements of the plants are consistent and which are changeable, and we shall arrive at an exact knowledge of the sum of all the ingredients we withdraw from the soil in different crops. With this knowledge, the farmer will be able to keep an exact record of the produce of his fields and harvest, like the account book of a well-regulated manufactory, and then by a simple calculation he can determine precisely the substances he must supply to each field, and the quantity of these, in order to restore their fertility. He will be able to express in pounds weight how much of this or that element must be given in order to augment its fertility for any given kind of plants. These researches and experiments are the great desideratum of the present time. To the united efforts of the chemists of all countries we may confidently look for a solution of these great questions, and by the aid of enlightened agriculturists we shall arrive at a rational system of gardening, horticulture, and agriculture, applicable to every country and in all kinds of soil, and which will be based upon the immutable foundation of observed facts and philosophical induction. End of section 15.